I think it works, right? Okay, good. Let's get started. So today we're gonna learn about electricity and then charges, electronic charges. I think this will be easy for you. So can relax. I'm supposed to one thing. So one of you asked the TA that it's okay to pick some game about basketball. I don't know. There's a game. It's called Mini Hoop. You know this game? I don't know, but it's a basketball game, and then you shoot a ball on a computer, I think, and you try to put the ball into the basket. So it's basketball, right? And he asked me, it's okay to pick this game as a topic. When sure, it's okay. It's any topic is okay, but the important thing is to include physics in it. So even if you pick that basketball game and you don't include physics, the grade is not good, right? But if you explain the physics of the basketball very well, then you get a good grade. So the point is how much physics you can include in your presentation. Maybe Einstein is a good topic. If you pick Einstein, Einstein did a lot of great physics discoveries, theories, right? So you can pick any topic. There are a lot of topics related to Einstein, so that's easy to introduce. What is general relativity, Brown motion, special relativity, right? Okay, something like that. Okay, so is there who asked the question about basketball? No, he's not here. Okay. All right. So let's get started. So. Okay, so this today's topic is easy about electronic charges. Okay, let's get started. And then this is not working. How come this is not working? Okay, I need to go to PowerPoint to do that. Oh, it changes. Did it change? Yes. So electronic charge is the positive and the negative, right? Plus and minus, right? Maybe everyone knows about it. Then charge is quantized. It comes only discrete amount. So plus 1, plus 2, plus 3, sometimes there's no plus 1.5 or plus 1.7. We don't have that, right? And then all photons carry the same positive charge. All protons, not photons. Protons carry the same positive charge. Protons comes with plus 1, right? And then this is and then charge of the plus 1 or minus 1 is elementary charge. We use this E, right? Then all electrons, on the other hand, carry the negative charge, minus, right? Then which is equal to the proton's charge. So it's same amount, plus E minus E. The quarks, which make up protons, neutrons, and then many other particles, carry plus minus 1/3 or plus minus 2/3, but they cannot, exist by itself. So they combine to make particles like these. So all charges are in a discrete numbers. Is it a little hot here? Can I put the AC here? Is it broken? Okay. Is there any more AC? Is that on? Okay.
Oh, that's on.
If you see green light, that's on. I think it's not on. Is it turning on? Okay. You took my class before. ask before you let me?
Yeah.
You got a good grade, right? I
Yes.
remember. So why you came back?
I want to learn physics too. With you.
Oh, sorry. You took the other class.
Yeah.
Oh, okay, good. Welcome back. Welcome. Good to know. Good to know someone. You're welcome to take my classes next year or 2 years later. You're welcome to come back. Okay, then next. Okay, charge conservation. So your charges do not disappear suddenly. Okay, there's a conservation here. Net charge of the system is the algebraic sum of individual particles. Electric charge is conserved, so that's good. It doesn't disappear. Charged particle may be created or destroyed in pairs of equal and opposite charge. The net charge always remains the same. So if plus is created, the minus always should be created, right? If plus and minus disappear together, that's fine. But then only plus disappear or only minus disappear, that doesn't happen. Okay? The SI unit of charge is the coulomb, which is this number. And then the E is approximately how many coulombs? How many coulombs? How many coulombs? How many coulombs? Okay, what's the name? Huh? Alex. It's not your name. Your English name? Brittany. Bernie. Benini. Welcome, Benini. Okay. So here, the coulomb is 6.25 times 10 to the minus 18 E, right? So then E is, how do you calculate E? Maybe it's different number. How do you calculate E? So this one coulomb is this E, right? So one is yes, did you say minus 19? So minus 19, right? So you just take the 1 over this number and then you get how many coulomb is E, right? Okay. Then let's go to the next. Now we go to the Coulomb's law and the electronic force. So Coulomb's law is here. Coulomb's law. Like charges repel. So the same sign of charges repel, plus and plus repel, right? And then plus. So then opposite charges attract. So is attract, right? Maybe everybody knows about that. Then with a force that depends on the product of the two charges. So that is Q1 and Q2, those are the product of the two charges, right? Then it also depends the inverse square of the distance between them. So distance between them R squared, and that gives you the force. The electronic force that a charge Q1 exerts on Q2 is given by Coulomb's law. So that's this. And K is the constant with some number, this 10 to the 9 times 10 to the 9, something, and R is a vector, shows the direction. Let's look at the figure. So plus, and then plus is going to, repel, right? So the force is going this way. And how much force? How big is the force? Is the product of Q1, Q2, you can calculate. And also depends on the square, inverse of square. So of course, if this charge is large, then you have a bigger force, right? Then also distance here, R squared, right? So this already tells you electronic force is not big if the distance is large. If distance is large, this is going to be a very small number, right? But the opposite is true. If the distance is very small, this number is going to be very large, right? So that's why electronic force is very important in micro scale. It's not so much important in our human scale. Because we don't feel it like, oh, there's a positive charge, oh, I push, we don't feel that, right? But it's a big force for electrons and small particles. I mean, you can see that already here. If the charges are in opposite opposite sign, plus and minus, they attract each other, right? But then the equation of this is going to be the same. Again, the closer the force is bigger, and if the charge is larger, then the force is nothing complicated. Right? Then a superposition principle. This is super convenient, right? If we have multiple charges, like here, plus Q1, plus Q3, and minus Q2, and then, okay, say if you're Q3, how do you feel the force? Then you just add the superposition principle. That's super convenient. So this way, then this way, and then this way, right? Then you add it in a vector, right? So you amount of this, amount of this. Okay, so that's called superposition principle. Yeah. Okay. So this is easy. If you want to calculate mathematically, it's easy. Okay. Roy, what is superposition principle? He's Roy, no?
It's cash.
It's S.
Cash.
Cash. What is superposition principle?
Sorry.
What is superposition principle? Okay, if you want to do some other homework, please do it in the library. You don't need to stay here. If you want to come here, please listen to me. Is that fair? Yeah, but then you're not listening to me at all. Right? I don't know. If you want to stay here, please listen to me. If you want to keep doing that, please do it in the library. I told you this before, right? I told you that's right. Okay, no problem. Okay, then electronic field. Okay, the physics field is a very common idea in physics, right? So electronic field at the point is the force per unit charge. So electronic field is something, if you put plus E, then how this charge is going to feel. The force that this charge is going to feel is the electronic field. So E is F divided Q. So if you put one, so the force divided by charge. So that's unit charge. If Q is 1, then that field is the force is the electronic field. So then the force on the charge Q is an electronic field. Okay, this is the same thing. So if you go back in Coulomb's law, here you put the E, one unit charge, and then what's the force? That's the electronic field of the position. Okay, then the electronic field is analogous to the gravitational field, which gives the force per unit mass. So here's an example. There are two examples. So here's an electronic field, and then you put the point charge, and then what's the force you feel is the electronic field. This is another example of the electronic field from a point charge. So if you have a plus charge here, and then you put unit charge here, you feel this kind of force, right? So if you put plus, then you feel the repelling force, right, towards direction that away from this charge. So that gives you an electronic field. Now, as you can see, in this case, if you're close to the discharge, electronic field is stronger. Because of the Coulomb's law, distance squared. If you're away from the charge, the electronic field is smaller because of the distance is greater. Okay. So right. Okay. Then you can see it in the density of these arrows. So if you draw arrows in this way. If the density of the arrows are higher, then that means electric field is strong. If the density of arrows are sparse, then electric field is weaker. Okay, I already spoke about this, but if you have a point charge, then electric field is in a radial direction like this, depending on plus direction depends on the plus or minus because of this Coulomb's law. And then this already we talked about. This is superposition principle. So if you have multiple charges, then electric field also is a summation vector sum of all the electric field from all the charges. So if get one charge and another charge, then electric field also sums up, just like Coulomb's case, Coulomb law. Because it's the same, right? It's just electric field just for point charge. So both of them, superposition principle is true. Okay, the dipole. Okay, it's getting a little bit more interesting. So electronic dipole is something in plus and then minus with the same amount of charge in a very close distance. In this case, it's the distance between those two are 2a. And then dipole is electronically neutral, but the separation creates an electronic field. So if you look this system from the distance, it's neutral, right? Because plus one and minus one, so the total is 0. But however, these are opposite signs with some distance, so there should be, of course, electronic field. For example, here there's an electronic field from plus to minus, right? Then, like here, another example is here. What's the electronic field here? Because plus it's going to have electronic field this way, minus is going to have electronic field this way. So the vector sum, superposition principle, gives a total electronic field is this way. Okay? Right? That makes sense? And then product of the charge and separation, this P, Q times D, is something called electronic dipole moment, which we will use it later again and again in this semester. And then, I already mentioned this, but from the very distance, its electron field falls off at the inverse cube of the distance, so it's going to be neutral. And then one example of this typical example of electronic dipole is water molecule H2O, and then in case of H2O, these H are slightly plus and O is slightly minus, right? So if you look at the system, it's plus and minus separated a little bit away, right? So it looks like a dipole. So that's one example. Okay. Continuous charge distribution. Okay. Now we've been talking about point charges. But what if they're continuous one? Say something like this. It's not a point charge, but it has some size, and then it has some charges here and here and here. And then then if you have something like this, there's some plus signs everywhere within this object. Then what's the electron field here? Then we can just integrate, right? It's very typical things to do, right? For one or two things, the countable things, we just use summation sigma. But if something is continuous, we just replace the summation with integration. So this dq here is the charges, a little charge in a small portion of the object. And then, of course, this is Coulomb's law, right? So if you integrate all over this object, then you get the electronic field here. Did I say everything? Integrating. Okay, you treat this dq as a point charge. Okay, that's good. One example. Okay, two examples. The electronic on the axis of the charged ring. So here's a ring, okay? And then electronic field is charged like this. So this ring is say I don't know. I think it's plus large q. The total charge is plus large q, and radius is a. Okay. And then what is the electronic field at p? Can you type it? So another example, second example, is electron field of an infinite line of charge. So here's an infinite line, and it's charged with the density of lambda coulomb per meter. So per unit meter, 1 meter, the charge is lambda. Okay. Then what is the electron field here? Point P with a distance 1. Okay, so maybe we take a 10-minute break here, and then I'll let you to think about this, and then someone who can explain it later here. Is that okay? So let's have a 10 minutes break, and then, yeah, please think about it. Okay. You all know what is the answer, right? The answer is here. But it's not okay just to write this down here. Actually, I wanted to explain. Okay, the answer is actually here. But the point is explaining. Okay, so let's have 10 minutes break here. So please come back at 9:20, and then hopefully two of you can explain this. You can discuss with your friends or team up. Right. Okay. Let's have 10 minutes break. Okay. Online people, you can also, try to explain. So see you in 10 minutes. You can, look at whatever. You can Google or look at the textbook. Okay. So see you in 10 minutes. That's good. You have a text. So you have an answer. Okay. You can, everybody, if you don't understand, you can ask.
Professor, you are muted.
Oh, okay, sorry. Okay, good. Can you hear me? I hope.
Yes.
Yes.
Good. Sorry about that. Then you did this integration, and then here x squared root, so that's what's shown up here. Right. So, okay, good. Then okay, let's move on. I'm running out of time. Matter in the electronic field. So if the matter the charge, something like this dipole, and then in an electronic field, say in this direction, it feels the force, right? In this case, in this example, if you plus and minus, you feel the force is this way. So plus is going to go this way, minus is going to this way. So this is going to try to rotate, right, aligning with E to feel the force. Yeah, and that's a force to rotate this. It's called torque, and then you can calculate with this torque. It's P cross EP. If you remember, is a dipole moment, right? Dipole moment is a distance times charge Q. So distance Q and then E. Then right, and also dipole in an electronic field, that's a potential energy is E times E, because it's potential energy, right? If you're holding this when you try to rotate, that's a potential energy in this amount. Okay. Then conductors. Okay, getting interesting. How many pages I have? Maybe I cannot finish. Okay, I have. Oh, okay. This is last page. Okay. Okay. Conductors, materials in which charge is free to move are conductors. So something like a metals are conductors, right? In this case, these negative electrons can move within a metal. So these are conductors, right? And then material is, and then if the material in which charge cannot move, it's insulators. For example, I don't know, rubber band. Rubber band, the electrons cannot move in the rubber band, right? So these are insulators. Then insulators generally contain molecular dipoles, which explain torques and force in an electric field. Yeah. For example, say if in a dipole, in an insulator, and electric field is upright, it might align, in the field of electrons, in the direction of electrons. Such materials are called dielectrics. So something like this. We use these for conductors. We showed examples of conductors later. Even if molecules aren't identical dipoles, they require induced dipole moments as a result of electron forces straight in the molecule. So, say if this is not dipole, but then if E is upright, and then because of the E, that if there's a slight shift of plus and minus, and then this looks like a dipole, right? Alignment of molecular dipoles reduces an external applied field. And then once you have aligned this dipole up here, this is going to counteract the electron field applied, right? Because in this particular part, there's a plus to minus is separated, so this electron field a little bit this, and this cancels out a little bit of E applied. So this reduces the electron. Okay. Now, so that's what we learned. It's I hope it was not too difficult, right? We learned Coulomb's law, superposition principle, and then we saw some example of wire to integrate. Okay, now is the fun part. Okay, we have a little bit of time, so let's look at because the topic, one of the side topic of this class is to use game to so online people, I give you the link here, so you can try here. How do I share this window? I'm gonna share this. Let's share this. This. Okay, now I need a volunteer. Okay, Sean, can you pick someone? Okay, please come here. Okay, now this is a game about Coulomb's law. Okay, so I think, so please try here, and then people, oh, careful. People can try, what's your name? Judy, you can try help Judy, okay? So Judy, your goal is put this plus charge into here, okay? And then you can use these charges and then put it here. So if you put plus here, plus and plus repel, right? So it goes move this way, right? So can you try? Let's see. I think this is level 1 or something, right? You can use mouse, no? Can do? Yeah, so yeah, put it somewhere. And then you can start. Then are you okay? This is gonna work?
Yeah.
Okay, start. Yes! Good, okay. Judy, can you pick someone else? Now we're gonna go level 2, okay? Anna, you up? Please come here. Okay, now you have a more difficult situation, right? Sorry. I have to reset. Okay. Clear, right? Okay. Now you have a blockade here. So you have to go something like this or something like this. Yeah, So I think you need to use the mouse. Can you use the mouse? Yeah. So this is an example. So the final presentation of this class is to create a game, right? So for example, if you can create something like this, and then explain about Coulomb's law, and superposition principle, something like that. So that's sort of good final presentation, right? And I hope it's going to be fun to play these games and then learn projects. And are you having fun?
Yes. No.
If you fail this class. Did you know that? Now it's not fun. No?
It's not. The same.
Okay, well, you put more. You can use more.
Okay.
Because you need to change directions, right? And then when you're comfortable, you can push the start. You're fine. Can I help? Can you say?
Oh, reset. Okay.
Oh, you want to start over? Yes. So, okay, this is about superposition principle, right? So the force electric field here is superposition of this and this and this, right? So it's gonna go probably like something like this, no? Anna, I don't think this is going to work.
No.
You need help? You can ask your friends to help if you like. There you go. Okay. We can work together if you like. Okay, we have one more level, so can you hurry up?
Oh.
You can put it here too, no? here, so that it comes here and here. No? Something like that, yeah. Okay.
E. I'm not sure. Maybe just try. Ah, I get it. Let's go this way and then go that way.
Reset. When you start, just please let us know so we know you're starting.
Okay.
That's a good idea because we won't go there, right?
Okay.
Okay. Okay, next person. Who wants to go next? Can you pick someone? Okay. Next up, Jayo. Okay, can we go to level 3? Because we're running out of time. This is too easy for you, right? Where's the mouse? I don't know. Let's go to level 3. Okay, this is good for you. Reset. Oh, Jayo. You have 2 minutes to finish. What's your name, by the way?
Clark.
Clark.
KLA. Clark.
Clark. Okay, Clark. Okay. Last chance. Has anyone succeeded? Oh. You can try with your laptop. Okay, maybe we can stop. Good. Okay, so just 2 people failed the class, but that's okay. We have still more students. So that's one example to use game in physics. Okay, maybe we should stop today's class here. So group 1, you guys, please prepare presentation next week, and then please put physics into the presentation. And then other people, if you haven't signed up, please sign up. Have you signed up? Okay. Make sure your name's there. Okay. And then I guess that's all. If you have questions, you can come to me. If you don't have questions, see you on Friday. Okay.
Professor, I have a question.
Yes.
Will you upload the presentations to the
Yes.
e-learn or to the
I will. I'll
Awesome.
upload and then send you the email.
Oh, okay, great. How about the game? Can we play the game in our house? The one.
Sorry.
The
Can
game that is.
Can you speak loud?
Oh yeah.
I cannot hear you very well.
Yeah, the game that you're playing in the classroom. Will you send us a link for the game or something?
Sorry, your voice is a little too small. Can you speak up?
Oh, yeah, the game that you were playing in the classroom. Can we
Yes.
find that game online?
Yes. Look at the link I sent you, right?
Oh, okay.
The message here.
Oh,
You see that?
yeah. Found it.
Okay. Yeah, so please try that, and then if you succeed, you can show us next week or Friday.
Okay, awesome. Thank you.
Okay.
Have a good day.
Try. Thank
Okay.
you.
Thank you. Bye-bye.
Okay. Any other questions? Okay. Online people, I'm gonna get out here if you don't have questions. So see you on Friday. Bye bye.
See you, Professor.